All right. So transparent. The bottom pane is transparent. The bottom pane is transparent, and its refraction, something we're going to talk about in the next unit, is why we cannot see clearly to it. But there is light getting through. That means it's transparent. And it has to do with resonance. Remember we talked about resonance. Remember the Comaneros bridge had the same frequency, natural frequency as the little gusts of wind in the Comaneros. Same idea is that our material has the same resonance frequency. The light coming in is the force vibration in the material. If it has resonance, it's going to be opaque. If it does not, it will be transparent. Anyone need more time on this one? Good? So, transparent. Things that are transparent. One, the light travels in a straight line through the material, through the upper pane of glass. It's going to travel through in a straight line. In a straight line. Even in the lower pane, they are traveling in a straight line. It's just the texture makes that line in a different direction. The frequency of light is not resonant. Not resonant. Okay, so it's not going to collected up. So glass is not resonant with visible light. You can also talk about what kind of light is going through, because just because you are resonant with one type means you're not with other. So it's transparent on that. Anyone need a little more time on that? So, in transparent material, the light is going to be absorbed and retransmitted from atom to atom through that material. This is easiest way actually to explain in the particle theory. It's easier to talk about a photon going in one side and coming out the other. Now the thing is, especially we talk about in the next unit, we're going to talk about Snell's law. And Snell's law talks about, the speed of light in a material. Now remember, what did we say about the speed of light? Does light ever have a speed other than the speed of light? No. However, they didn't understand what was going on, so they would say, the speed of light slows down. Well, can light slow down? Well, let's think of mechanical terms. If I had a high-power rifle and I took a tree, and I shot through a tree, my bullet will go through the tree, but when it gets on the other side of the tree, will it speed back up to its original speed? No. But see, in glass, if a photon enters that, it enters at 3 times 10 to the 8th meters per second on one side, and it seems to slow down going through, and it will come out at 3 times 10 to the 8th meters per second on the other. In other words, it speeds up. Well, that doesn't seem right. So is it this little photon boring a hole through the glass? No. Not what's going on. Something else. So what we're actually talking about is how fast can that energy be transmitted? It's the energy that's going through. Not the photon, not the energy. The photon that goes in is not the photon that comes out. Although it is the same energy. Same energy, different photon. Same energy, different photon. Anyone need more time on that? Now, the thing to keep in mind in matter, if I look down on the atomic level into your tables are mostly what? A lot of S word in between things. Empty space. Yeah, there's a lot of space. Nuclei of atoms are very, very, very tiny. Even in what we call solid matter, there's a lot of space in between those nuclei. There's a lot of space in there on that fully fit together. And it's that space that we're going to be jumping across. Anyone need more time? So our photon comes in, and it's going to hit this first atom. And in our particle theory, the little electron absorbs some energy. It will pop back up to a higher energy level. But electrons are lazy. They do not like to be at higher energy levels, and it's going to go back down and spit out a photon. However long that takes depends on what the material is. Some materials take longer than others. So it comes up here. It jumps up a little, jumps down and holds it, but it's not resonant. Remember, it's not resonant. Not resonant. And so it jumps down and spits out that photon. Now from this atom to that atom, it's a photon again. It's traveling at 3 times 10 to the 8th meters per second. Hits the next one, goes up that energy level, gets held for a little bit, and gets spit out. Now it's a photon, 3 times 10 to the 8th. And it keeps doing that all the way across the glass until finally it gets to that last atom, and boom, it comes back out, traveling at 3 times 10 to the 8th meters per second. So the delay has nothing to do that this photon's not slowing down. It's the fact that every single time it's like they have to keep, it's like they're have to stop each time. It's like I go stop, go stop, go stop, go stop, go stop. So instead of like the freeway where you just get to drive, it's like going down Woodside Road where you have to stop at every single stoplight. And it delays you. That's what we have. That's what our delay is on that. As opposed to opaque. Opaque. The light and the material are resonant. Resonant. And the energy is absorbed by the material. Now, if you get absorbed, what's going to happen to my little atoms? I mean, before they were kind of moving like this, but if I'm absorbing energy, what's happening to them? They're going to start doing what? Moving more or less or the same? More. They're going to start moving more. Temperature goes up. Remember that average kinetic energy. Like today, when you go out to your car and you put your hand on the glass, is that glass going to be cool or hot? Hot. It'll be hot because it's been absorbing ultraviolet. Whereas glass is transparent to visible light, glass is resonant to ultraviolet. Glass absorbs ultraviolet and goes up in temperature. In other words, if we saw an ultraviolet frequencies, if our eyes worked in the ultraviolet and not in the visible light spectrum, these windows would look like that wall. It would look like a wall. You want to be able to see through it. Now the wall, what can we say about its resonance frequencies? It's resonant with what frequency of light? Can we see through it? No. So it must be resonant with visible light. It's resonant with visible light. Whereas, but see, different frequencies, different things going on here. Anyone need more time? Which kind of leads us to a special case, reflection. Now, metals will absorb visible light, somewhat. But in visible light frequencies, metals have a mirror surface, which means kind of like the outer layer of electrons will absorb it and then spit it back out, back at you. In other words, it sends it back to you, reflective. And this is caused by those outer electrons not being bound to the metal atoms. So in visible light, metal is our mirror. In fact, every mirror you have is made out of metal. And I bet you're saying, but my mirror is made out of glass. Well, look carefully at the mirror. Where is the reflective surface? Is it the surface of the glass or at the back of the surface of the glass? The back. And the back is coated with metal, usually aluminum, although we call it silvering. But originally it was silver. But it's metal, a very thin layer of metal. Now, does that mean other things don't reflect? Now, to be honest, the glass does reflect a little bit. In fact, if you look over here by the pole, can you see a little bit of reflection of the room in this right here where the post is? Because it's dark behind there. But I can't see a reflection because there's lots of what coming through the window? Light kind of washes it out. I can't see it. But if it was dark outside, what would I be seeing in this? Be seeing me, be reflective. You've all seen this at home. When you're inside at night, you can't see outside because you're getting a reflection back. Because the glass does reflect a little bit. Does do it a little bit. And this is how you make a one-way mirror, or a two-way mirror rather. Basically, you have a piece of glass, put a dark room on one side, a very light room on the other, and you can't see through it. Usually, they also might put, now modern ones put a little bit of microscopic layer of metals also, just to make it, you can see through it, but it helps that reflection on the other side. How do you tell the difference? Well, if I touch the mirror and I'm touching my fingernail, it's not a mirror. It's basically, there's probably something on the other side. Because a true mirror, if I touch the mirror surface, there should be a gap between my reflection and my finger, because the gap represents the width of the glass. I mean, the glass is there to protect the mirrored surface. So true mirrors, there should be a gap. Two-way mirrors, on that, some department stores have gotten in trouble for putting two-way mirrors in dressing rooms and things like that. Well, cameras, shoplifting, and stuff like that. They've gotten in trouble. I just out of curiosity always touch the mirror just to see. So, I haven't found one that wasn't a real mirror yet. But see, this is invisible light now, but in